Welcome to Astronomy State of the Art. It's one of our live sessions. I can't quite remember how many, maybe 8th or 9th?
The 7th.
7th, okay. We're open. I'm open for all your questions. There have been a good number on the discussion thread. I know a few hundred people have added actually since our last live session, so I do encourage anyone who hasn't participated in a live session to join and ask questions. That's what we're here for. It is a disembodied experience, an online class, but it doesn't have to be removed from all personal interactions. So let's see what you guys want to hear about.
Let's do a quick sound check. If you can hear us in the Udemy live session, please just say hello in the window. All right, sounds good. Well, here we go. So the first question is actually from the last live session, but it's from Julian, who is with us today. And the question is, what new technology in astronomy are you most excited by?
That's a good question. New technology, I think, I was excited about adaptive optics for a number of years because we have a research group that's working on that. And I'm still excited by that because it's coming out of its engineering phase into its purely astronomical phase. But I guess you wouldn't necessarily call that a brand new technology. I think the technologies that's most exciting right now is the technology that will lead to the detection of gravity waves, because that's a frontier that we haven't visited yet in astronomy. The ability to detect distortions in space-time traveling at the speed of light through the universe as predicted by general relativity. Essentially, by the way those space-time distortions alter a test mass, a large pure metallic rod carefully suspended and isolated from geological and human vibration and noise, at this incredibly exquisite level of 1 part in, let me get it right, 1,000 billion billion. So as far as technology goes, it's pretty hard to beat something with a precision of 1 part in 100 billion billion. And that technology has been test bedded at Caltech with the LIGO instrument, and it will come up in about a year and start taking science data with that level of precision, which is required to detect astrophysical signals. It wouldn't succeed if it was an order of magnitude worse than that. Like 1 part in 100 billion billion just won't cut it. So that's pretty much a preeminent technology that's going to be applied in astrophysics in the next decade.
All right, so the next question is from Will, and he asks, as far as our understanding of technological advancement goes, do you think we are ready to meet new life? And do you think this could change our understanding of our place in the universe? And this could be as simple as organisms or intelligent life.
So a really good question. Are we ready to meet new life or encounter it or just discover it? And it sort of depends on who the we is and are we ready and what the life is. So let me divide it that way. Astronomers and astrobiologists in particular, of course, have been ready and eager for this really for decades, because the SETI people, Search for Extraterrestrial Intelligent Life, they've been doing their work for over a half century, and they want to succeed. They're not in the business of listening for signals and hearing a great silence and just finding out that we're alone. They want to succeed in their experiment. As far as whether we're ready to encounter life on another world, there's an interesting question in the local universe. So one of the possible places we might discover life is within the solar system. That could be on Mars, which we are visiting fairly frequently over the next decade with robots, and then perhaps with humans and astronauts in about 10 or 15 years. Or that could happen on Europa or Titan or Enceladus or a handful of other places where all the ingredients for life exist. Now, if we find life, especially on Mars, the nearest of those locations, the question of whether we're ready for it is quite interesting, because we have to do two things. We have to be careful not to forward contaminate Mars, which is to say we have to be careful not to bring organisms to Mars that just naturally attach to the spacecraft, and many of which, or some fraction of which, survive the intense vacuum and ultraviolet radiation of the journey to Mars. If those organisms, contaminate the Martian regolith, soil, where the probes land, then we may not have a clean experiment of the detection of life on Mars. So that's a serious concern. So being ready to detect life on Mars means actually being ready to have fully and completely sterilized spacecraft doing the work. Eventually, the debris we leave on Mars does get sterilized just because of the thin atmosphere and the cosmic UV radiation and cosmic rays. But as we arrive on Mars with a new mission, there are microbes that survive the passage, lots of them inside in interior regions of the probe, and even some small number on the outside of the probe. So we need to be ready in that sense. We have to actually learn how to sterilize and do a pure experiment of life detection. Now, if we bring samples back from Mars, which is planned for 10 to 15 years, we have another issue of preparedness, which is what's called forward contamination, back contamination, where we bring the samples back. We faced this issue already with the Moon. So when the 472 kilos, as I recall, of moon rocks were brought back by the Apollo missions, they went to a secure facility at Johnson Space Center in Houston, where essentially 95% of those rocks are still maintained. Very secure. I think it's called a level, what would be today a level 3 or even level 4 biotech facility in terms of cleanliness and vacuum and the inability for humans to encounter the samples without a lot of provisos and preparation. So we would obviously ratchet that up a notch. The plans for Mars sample return would take that preparedness up to a level of 5 in biohazard containment. And that's the worst. That's the sort of highest level of risk, if you like. Hemorrhagic fevers or the worst kind of pathogens that we have to deal with on Earth are subject to level 5 biocontainment. And we'll use that level of safeguard for Mars rocks if they come back to the Earth. Because if those microbes are not like our form of life, there is indeed the distinct possibility, realized in science fiction of all kinds over the decades, that they could be the perfect pathogen that might wipe us out. That's a worst case scenario, but you have to take it seriously since we don't know what's there. So being ready to detect life on Mars means those two things: being ready not to mess up the experiment by what we bring to Mars, and being ready to deal with the samples that come back that might have microbes in them of unknown function and form and unknown impact on our biosphere. So that's one level of preparedness. The preparedness, and I think the average person is not too animated one way or the other about whether there are microbes or not in space, but they're certainly animated about the fact that if we bring those microbes back, they could impact us negatively. So I think people are quite happy that NASA is being extremely conservative on this. The other aspect of preparedness, are we ready to encounter life in the universe, comes from intelligent life. And I'm sure many of you have read the comments by Stephen Hawking, maybe 2 years ago now, where he basically said we should not be broadcasting our presence. We're doing a lot of passive listening experiments, but there are some broadcasting experiments going on. In fact, the private sector, which is not bound by government regulation of any kind, has the capability to beam signals out into space. I think as a private citizen, you can spend thousands of dollars to have your own message sent to a nearby star, which may or may not have planets around it. So this stuff is happening anyway, whether we know about it or not, or like it or not. And Hawking's argument, which is moderately logically grounded in what we do and don't know, was that it's based on the timing argument that any civilization we encounter, given that we're in our infancy of being able to interrogate space or travel beyond the solar system, is likely to be much more advanced than us. And to his mind, since we've used a lot of our powerful capabilities as humans to cause harm and mayhem to those of our kind and other species on the Earth and the Earth itself, he just imagines that life out there that's intelligent and advanced might also be kind of nasty or brutish in some way. And he thought, it's better that we don't know. It's better that we don't ask, and it's certainly better that we don't broadcast our presence and inadvertently reveal ourselves to a superior intelligence that might be malign in their disposition towards us. And that's one perspective. The other perspective is the perspective of the SETI researchers who just say, no, we need to know this because it's our signature that we're not alone in the universe. A future civilization or a more advanced one will undoubtedly or very probably have solved some problems that we haven't yet solved. How to make abundant, clean energy, for example, perhaps how to get on without intertribal squabbles and endless wars and skirmishes of all kinds. That's an idealistic scenario, but there's some hope that a civilization that survived the rocky passage we're going through might have reached a more benign place, a place where they could educate us and inform us and enlighten us and sort of bring us along towards a higher level of awareness, consciousness, and knowledge. So that's the flip side of the coin. And there's really not many arguments in between. You'll read the apocalyptic scenario and this Hawking type comment that we really don't want to know, we're not ready for it, it'll be bad news, and so we should just be really cautious and not wish that this experiment succeeds. And then the researchers who just figure this is discovery, we could be enlightened by it, we could be saved in some sense by it, whether or not most of us think we need saving, that's a possibility, and they just want to bring it on. They want it to happen as soon as possible. You find very little comments in between. So everyone who's listening or everyone thinking about this can judge where they stand on this issue.
All right, our next question is from Julian Onions, and they ask, one of the cosmology parameters I just can't seem to understand is named sigma 8. Can you explain what it is?
Yeah, sigma 8, this is now in the technical, not in the weeds, but in the technical area of observational cosmology. Sigma 8 is a measure of clustering. It's a measure of the degree of clustering. So when you're discriminating between cosmological models, which include normal matter and dark matter, the amount of matter, of course, affects the rate of clustering and the formation of large structures. And so, but clusters form on all different scales. If you look at these gorgeous maps of large-scale structure produced by the Sloan Digital Sky Survey, there are definitely big, globby, centrally concentrated clusters like the Coma cluster. But most of the structures of the universe are a little more diffuse and they're elongated. They're not really spherical in shape. And the large-scale structure of the universe as a whole has this sort of filamentary or sheet-like structure with voids in between. So characterizing structure in the universe is not simple because it has these different scales. It's a multi-scale phenomenon, as we would say. Sigma 8 is just the handy single number by which astronomers calculate the amount of concentration of normal and dark matter in the universe. So sigma is just the variation. It's a variance that leads to a 1 sigma fluctuation in the positive direction of an overconcentration of matter. So you can think about structures in the universe forming where there are overdensities and underdensities. So in the universe, as the mass moves around and forms structures, there are obviously some areas that are cleared out as well as others that become more concentrated. So in terms of sigma, which is a fluctuation, like a statistical fluctuation, you can have overdensities and underdensities. Sigma in this sense refers to a 1 sigma, or in a bell curve, 67th percentile fluctuation in upward direction, and the subscript 8 refers to 8 megaparsecs, roughly 25 million light years. So that's a sphere 25 million light years across, which has been subject to a 1 sigma upward fluctuation in density caused by the growth of structure and gravity operating over 13 billion years. And if you measure, you can measure this in the universe. It's an observed number, so you can say what our universe, on average, in a 25 million light year across, in a 25 million light years across sphere, what is the average upward fluctuation of density? And that number, it can be observed, and that number is also predicted out of theories. And so if the type of dark matter changes in the theory, or the amount of the dark matter changes in the theory, sigma 8 predicted by the theory varies. And so it's a point of comparison with dark matter, cold dark matter theories, and a very important one, actually.
All right, next question is from Wheeler. Isn't it actually unknowable as to the question of the universe being infinite?
It may indeed be unknowable because, infinite space as a concept is essentially unknowable, because how can you verify that something was infinite? So even in principle and philosophically, it's unknowable. In practice, it may also be unknowable too, because observationally, so there are two aspects to the size of the universe and the possibility that it's an infinite. One is the observational aspect, and the other is the theoretical aspect, and maybe the third is the philosophical one. So I've dealt with the philosophical one. Philosophically, you're correct, it is unknowable. Observationally, it's also unknowable because we are bounded in our view of the universe by the distance light can travel in the finite age of the universe. If the universe were very much older than it is, say the universe were for some reason 1 trillion years old rather than 13.8 billion years old, light could have traveled through vastly larger regions of space to reach our telescopes currently. And so we could view a universe vastly larger than the one we see. Instead, we see a universe where the distance to the horizon, or the limit that light could have traveled in the age of the universe, is about 46 billion light years. And that factor of 3, the fact that we see 46 billion light years in any direction in a 13.7 billion year old universe, is because the universe was expanding faster than light for a lot of its early history. So that is the limit, and that is just an absolute operational limit to our visibility in the universe with telescopes. So observationally, we can't decide the proposition either. We cannot discuss whether the universe is infinite or not, because all we can say is that the observable universe is this very particular size. And that very particular size, of course, gets bigger every year. As we wait longer, then we see into more and more distant regions of space. So it's not a fixed number. As time moves on, the observable universe gets larger and larger. Theoretically, what does the model say? And that's interesting, because the Big Bang model, as modified by the inflationary idea in particular, which has some verification now in the microwave data, in that model, the physical universe is going to be very much larger than the observable universe, that 46 billion light year distance in any direction. The factor by which it's larger is very much a function of the type of inflationary theory you subscribe to. And although the general idea of inflation, which is a very rapid exponential growth in the universe size in the first tiny fractions of a second after the Big Bang, although that generic idea has confirmation by microwave observations, the nature of the entity, the force, if you like, or the field that caused that exponential expansion is not known. And there are literally dozens of inflationary theories. And depending on which theory you pick, the physical universe, the space-time of which we're seeing a tiny part, could be hundreds or thousands or millions or trillions of times larger than the observable universe. That's a pretty big range. Do those theories allow the possibility that space-time, however we want to think about it, in a fundamental sense, is infinite? Yes, they do. And the theories, they can't put infinite space-time in as an ingredient, because the infinity of the space doesn't really make much sense. For example, gravity or any force that doesn't decline to zero, that has an inverse square law, will be infinite in an infinite universe. This is a problem Newton had with old-style gravity. So the theories don't put in an infinite universe, but they certainly accommodate a universe that's so vast compared to our observable universe that operationally it might as well be infinite.
So Alice Amanda is interested in how robots may take over from humans, and she asks, do you think that Android-type robots will take over from humans as far as space travel is concerned, but then more generally about how robots will, the role robots will play in future space exploration? Right.
So it's a great question, because it's an argument that space scientists in particular and astronomers have been having for decades. In the very practical sense, we use robots to explore space already, and they do an excellent job. So a lot of the big debates in the planetary science and space science community are over the enormous cost of sending people to space, and that's even into low Earth orbit. Of course, we know each shuttle launch, when properly costed and fully costed, was something like $500 million. It's a lot of money, and the shuttle never went up as much as it was supposed to, and that's just putting people into near Earth orbit. The Apollo missions taken to 2013 dollars are about $60 billion. That's a dozen people setting foot on the moon. So human exploration of space is extraordinarily expensive, and the price tag on going to Mars in the cheapest way you might do it, even a one-way mission where they die there, is still going to be more than that. It's probably $100 billion. Compare that to the cost of these very clever robotic probes. $1 billion or so, a couple of $1 billion gets you landing on Titan with a robotic probe 1 billion miles away. That's an extraordinary achievement. We've got Mars missions that cost a fraction of $1 billion that do extraordinary, clever things there. So robotic space travel, in simple terms, is hundreds, at least 100, and maybe hundreds of times cheaper than going to that same place with people. So for people who do this for a living and realize that society is not going to pay an enormous amount for this activity, it's a no-brainer. You use robots every time, and technology is completely on our side. Now we have nanobots, as you've, I'm sure, been reading just in the press recently. There are we finally, after decades of technology trying to do this, we've got miniaturized insect-level robots. The miniaturization level of electronics and cameras and sensors is now down to take them to millimeter scales. And so space travel, where the costs are really involved in fuel and getting to a high speed to minimize that travel time, and once you go beyond the solar system, that becomes the dominant issue. These things are made vastly easier by miniaturization, nanotechnology, and so for people who are, in a visionary sense, thinking of going beyond the solar system to the stars, they cannot see it possibly being done except by miniaturized robots. And the pioneers of this field are working on plans for this. There's a fairly advanced plan from some people, including NASA researchers, to send fleets of nanobots to Proxima Centauri, where we may indeed have the nearest Earth-like planets. That will be found out literally in the next couple of years. And if there are indeed Earth-like planets in essentially the nearest star system, people are very excited about just doing the experiment to go there. But it won't be us going there. It'll be really tiny, miniaturized robotic probes. So for most scientists and space scientists, there is no argument. You're better off with robots. Okay, but I deflected away from the core intent of the question, which is whether these robots of whatever capability might replace us. So I think they will and do already replace us as far as space exploration goes. That was the gist of what I was trying to say before. Now, more generally, could they replace us? And that does, if that's ever a prospect, it's receded to decades away. There are the people like Ray Kurzweil, who are extremely savvy and brilliant technologists in their own right, who are fairly convinced that the singularity will occur. A singularity is the projection of the time when robots, or androids if you like, will have human-like capabilities in every aspect, in their intellectual aspect, conscient, sentience, sensory, etc. There's no evidence that that's on the horizon or around the corner. So people who are extrapolating our rates of progress to say that in 30 or 40 or 50 years there will be robotic entities that are fully human capable and fully human equivalent, they're making quite a lot of assumptions, some of which just may not be valid. And they're also extrapolating technologies into realms where technologies have not been successful so far. So while it's easy to take Moore's law and project that, and indeed there's a sign that we can continue our march of the speed of computers and their miniaturization, there's no particular end in sight to that, especially with quantum computing. There are serious limitations in our abilities to have computers, which are enormously powerful, be able to function like humans, to think like humans in any particular way. Neuroscience, not my field, is obviously, a great science of the 21st century because we're in the baby steps phase of it. We really have made very startlingly little progress, in a sense, of having computers mimic the profound capabilities of the human brain. So personally, and of course someone like Ray Kurzweil would vehemently disagree, I don't think that possibility of humans being usurped by computers, or computers or androids, whatever you want to call them, having quintessentially human equivalent capabilities it's neither on the horizon and certainly not around the corner, and I'm not even sure it may ever be possible. But if it is, we're talking 50 or 100 years, and some very profound revolutions in neuroscience, some really very difficult and intractable at the moment technical problems would have to be solved for that to happen.
All right, and the next question is from someone who I don't believe has been at one of our live sessions before, so welcome, Jury. Thank you for joining us. Jury asks, what is the difference between dark matter and dark energy?
They're both very enigmatic. So astronomers are, in a mature phase of their theories of the universe. The Big Bang has been around for 60 years and has been receiving ever more verification from microwave satellites and other observations. So we have a very mature and well-tested theory of a hot, dense, early phase to the universe. But the universe as a dynamic entity, the expansion of space-time, is governed by two quantities, two things, and those are dark energy and dark matter. And we're really in some ignorance about both. Our ignorance about dark matter is not quite as profound as our ignorance about dark energy. So let's just start and briefly summarize for dark matter. The dark matter is having ruled out all sorts of other possibilities like black holes and substellar objects and dust in space and so on. It's almost certainly going to be a fundamental microscopic particle as yet unseen in physics labs, but anticipated in physics labs. Dark matter may actually be detected in the next 3 to 5 years by deep underground mine experiments looking for new types of fundamental particle. So that's what people expect, that's what physicists expect, as well as astronomers. And that material, that stuff, is defined as dark because it doesn't interact with radiation. So it's a requirement of the dark matter particle is that its interactions via the electromagnetic force are either weak or absent. And that stuff exceeds the normal stuff, that is the normal atoms, electrons, protons, and neutrons of the universe, by a factor of roughly 6. So that's of order a quarter of the universe in dark matter. And the strands of evidence for the existence of dark matter have not been around quite as long as the Big Bang model, but almost as long. The first evidence for dark matter emerged in the mid to late 1970s, and it's just got stronger and stronger and more diverse in the nature of the evidence over the last few decades. So no astronomer doubts that dark matter exists. The only little gap in the argument is the possibility that our theory of gravity is wrong. If you alter Newtonian gravity in fairly subtle ways in terms of how the force changes with distance, you can sort of explain away dark matter. And so, to be honest, intellectually honest and fair, theorists especially have kept their eyes on other theories of gravity that could do away with the need for dark matter. If you go down that road, however, it's interesting. First of all, you're jettisoning an incredibly successful theory of gravity. Newton's theory, even as an approximation for Einstein's better theory, in the realm where it applies, has been very well tested and passes all its tests exquisitely and in many, many ways. So theorists are reluctant to throw away that theory of gravity. The other interesting thing is if you alter the theory of gravity to change the force law, which is really what you would have to do to explain away dark matter, you lose some of the beautiful and elegant properties of Newtonian gravity. So without getting technical, it's sort of Newton's law is a physical version of something called Gauss's law, which applies to forces of any kind that have an inverse square dependence. And there are certain elegant attributes of these force laws which are lost if you deviate from an inverse square law. So basically you make a pretty ugly theory if you do away with Newton's theory, and therefore, giving a lot more detail maybe than is required, people are accepting, astronomers accept that dark matter exists and they're just waiting to detect the particle. That's a pretty good situation to be in. That means an enigma of 30 or 40 years standing may actually be solved in the next few years. So astronomers are upbeat about dark matter, that it exists, that they've not been fooled, and that we might actually understand the physical mechanism or entity that is dark matter. For dark energy, the level of uncertainty is much higher. Dark energy is the component of the universe that slows down the cosmic, dark matter is the component that slows down the cosmic expansion over time. But for the last 5 billion years, the universe seems to have been accelerating in its expansion rate, and that's imputed to be because of this thing that we call dark energy. And dark energy is just a phrase. It's not a physical explanation. It's not a theory even. It's just a phrase to encapsulate ignorance at some level of something that operates the way Einstein's cosmological constant operates when he first solved the equations of general relativity. He had a term in the solutions that was possible that could lead the expansion to accelerate with time. And that seems to be what we've been observing. So the entity that causes this is called dark energy. It's twice, if you were to compare the two head to head, it's twice the influence of dark matter, which is why the universe is accelerating rather than decelerating, as it would if dark matter was dominant. And the evidence for the existence of dark energy and its effect on the universe really comes from only one direct observation of a distant supernovae being unanticipatedly faint by about 30%, which was inferred to be because space-time had expanded faster than the normal Big Bang model would allow, and that extra expansion rate or acceleration was laid at the door of something called dark energy. So what is dark energy? It's a repulsive force operating everywhere in space-time that increases the expansion rate. Now there are, I don't even know the number anymore, there are hundreds of dark energy theories or ideas. I would say theory is a little too nice a word to describe some of the ideas for dark energy, because we're in a state of pretty high ignorance physically. The theorists in physics are having a wonderful time because dark energy is something new in the mix, something that there's very little observational constraint on, so their imaginations and their theories can run wild, and they do. So the research literature is filled with extraordinarily exotic ideas about dark energy based on, as you might anticipate, string theory, quantum gravity, all sorts of things that only can be manifested in the very early universe, where we don't have a lot of experimental data, so that's why they're free to speculate. And as we speak in 2013, there's no concrete idea of what dark energy really is. No agreement at all, no theory that seems favored over other theories. So that's a slightly discouraging situation theoretically. Observationally, it's also a tough situation, because while the evidence for and the detection of dark matter grew steadily over 4 decades, such that we know the kind of dark matter potential around most galaxies, including our own, and we showed that all galaxies have dark matter, and we've seen the shape, we've literally made dark matter maps of the universe now. For dark energy, we have no such level of detail. The best we can say at the moment is that dark energy doesn't change its strength or its influence over space and time, which makes it akin to Einstein's original cosmological constant. People are trying really hard to get a few more handles on dark energy, one of which is called the equation of state, which is just a general physics notion for describing a fluid or a force or a dynamical entity and how it behaves. But even that is going to be 3 to 5 years work to get the equation of state of dark energy. If dark energy were more interesting in its behavior, if it decayed with time, if it varied over space, if it varied over cosmic time, then we'd have a lot more idea of what it might be, but it doesn't. It actually behaves very simply, almost as the simplest possible behavior it could have in nature, and that's actually limiting our ability to understand what it is.
Okay, our next question is from Mark. He asks, is the external occulter technology still considered, that is, to place a shade in front of a telescope to block a star's light and create more contrast between the star and the exoplanet?
Yes, so the question is a good one because that's a technology that has been under study by NASA for a decade or more. The having an external occulter in space is an obvious and a great thing to do, because when you're trying to make images, so the science behind the question is, of course, imaging exoplanets, and in particular imaging Earth-like exoplanets, where you're trying to look for the feeble, which is to say, billion times fainter reflected light of the Earth-like planet compared to a star, which is sitting very close to it in angular scale. And that doing that on the Earth and on the ground with the atmosphere, even with the help of adaptive optics, is extremely difficult. Nobody has demonstrated that they can do it. We have an instrument here, which we hope will do it on the Large Binocular Telescope, an Ulling Interferometer, which is going through its initial design and construction, and we hope in 3 to 5 years we might be able to do that from the ground. But in space, the whole thing is much, much easier. It's not just the Earth's atmosphere, it's also the stability of the space environment, because anytime you're trying to take an external occulting disk or structure and perfectly align it and keep it perfectly aligned, the optics have to be not just perfect optics, but also stay in perfect alignment, then you want the most controlled possible environment. Unfortunately, terrestrial telescopes, ground-based telescopes, are the worst environments because their temperatures vary by 30, 40 degrees Fahrenheit over a day-night cycle. The telescopes are moving in the sky and they're suffering mechanical flexure, just the distortion of the mechanical elements by gravity. And in space, you're not immune completely from the varying radiation of the sun, but you can radiate that energy away very efficiently into the vacuum of space. So in space, you can keep an extraordinarily stable environment. It's thermally stable, it's mechanically stable, it's optically stable. And so that's the perfect place to use this occulting technology. And in proof of concept, it's indeed not too hard to occult a central star to the level where you can have a contrast ratio, because that's what you need, of 1 billion to 1 for a nearby source of light, the reflected light of an Earth-like planet. So yes, in the current NASA proposals, there are several designs, there are actually a couple of different mission concepts that use an external occulter, and that's really an essential ingredient for characterizing Earth-like planets. The unfortunate tagline on that is that none of those missions are funded right now due to NASA's budget problems.
Right, the next question is from Alice, Amanda, and it's actually from a previous live session, but I want to make sure we get to it. And the question is, will wormholes remain science fiction, or are they something that may be found in nature in the future?
Yeah, good question. Matthew, when you said, for a minute I thought you said it's a question from a previous life.
Right.
Oh, okay. Alice, Amanda, you didn't tell me that you'd been coming several times round through the loop on this reincarnation thing. You were asking questions in multiple lives. Why not? We can ask questions in the multiverse too. Wormholes are an interesting concept. You may have read, or others of you may be aware of, a great book by Kip Thorne. Kip Thorne is a professor of physics at Caltech. I mean, he's a really high-profile, extremely esteemed gravitational physicist. And he wrote a popular book on black holes. I think it may even be called Wormholes and Curved Space-Time or something. I think Wormholes is in the title, probably 5 to 6 years ago. A really good popular book because he's writing from the Olympian heights of gravity theory, so he absolutely knows what he's talking about. And so he's fairly cautious about when he ventures into speculation and marks that point. He would say that connections, so we live in a simple space-time. One of the interesting features of the universe we live in is that space-time is essentially flat and uncomplicated. That's a little bit of a disappointment in a sense, and we think that's due to inflation, that space-time was stretched out to near Euclidean flatness in 3 dimensions. So the space-time we live in is flat, and what we would say is, in a topology sense, simply connected. So if you draw straight lines through the universe, they never intersect each other, and they stay parallel, and they don't disappear and then suddenly appear again. The exceptions to this, of course, are any place in our universe where there's a black hole, where that information is suddenly lost. And at that point in the theory, as far as black holes go, it's just a sink. It's a sink of information, it's a sink of radiation, a sink of particles. So when something is lost from the universe by going beyond the event horizon of a black hole, it essentially disappears from our view, from our diagnosing it with observations. But it's possible in gravity theory to have spacetimes that are more interesting and convoluted than our spacetime, that are so-called multiply connected spacetimes, where spacetimes connect to each other. And it's even hard to visualize this. We might sort of try and visualize a black hole as the usual two-dimensional situation where you distort a sheet and you pinch off a part of the sheet. And then you might try and visualize another sheet somewhere else with its own pinched off region, and you connect those two pinched off regions and thereby make a connection between those two-dimensional spacetimes, those sheets. And that's sort of a two-dimensional analog of a wormhole. Now, what would a three-dimensional space-time wormhole look like? Well, obviously you can't visualize it in that simple way because we inhabit three dimensions. But in theoretical terms, it would function the same way. It would be a place in our three-dimensional universe where there was a loss of information, we could call it a black hole if you like, and that would connect to a distant or a remote or disconnected point in space-time where that information could potentially and possibly be transmitted. So that's the concept of a wormhole, and it's a completely sensible gravitational concept. It exists in the theory. We're just not sure whether it exists in our universe. And in our proximate universe, it's of course very hard to test because we can't play with black holes. We can't do experiments with black holes. The nearest black holes that are collapsed stars are dozens of light years away. We got a beefy black hole in the galactic center. It's 27,000 light years away. This same issue of wormholes now applies to the whole cosmic scale, because while our space-time in the observable universe is this flat, kind of boring, simply connected space-time, space-time beyond that, the space-time that I was alluding to in the previous question about how physically large the universe could be, that doesn't have to be simply connected. That could be multiply connected and could have fissures or ruptures or connection points between space-times by passageways that you might call a wormhole. But that's beyond our observable universe. Again, something we can't test. So I would say the testing of the wormhole concept, which is a completely legitimate and valid concept in gravitational physics, that's worth saying clearly, it is really far away. We're struggling to prove the existence of an event horizon around a black hole. That's the next frontier of black hole physics. And we really have no idea, even in principle, how to do an experiment of depositing, say, information in a black hole and interrogating whether and how that information may manifest in some other part of space-time. That's what we want to do if we want to test the black hole, the wormhole idea. We can't do it yet. But maybe that's just, we have to wait a century. Maybe we'll get smart enough to do that in a few decades.
All right. We have another question from Alice Amanda. Have any black dwarfs been found, or would such a thing be undetectable against the blackness of space?
So black dwarf is a phrase that really talks about substellar objects. So let me just address the terminology here. The low mass stars, which are by far the most abundant stars in the universe, tend to be called red dwarfs because they're stars like the sun that are fusing hydrogen into helium. Actually, the very low mass end, all they can manage is a little deuterium. So they just actually do the first of the 3 steps of the fusion chain that the sun does. But basically, fusion is occurring in these very low mass stars. So their central temperature just pokes above 5 or 6 million Kelvin. But there's a very, very feeble rate of nuclear fusion. So at the low mass end of the normal star spectrum, you have objects called red dwarfs, and they're vastly abundant. There are hundreds of M dwarfs, as they're called. There's a classification scheme where the letter M is attached to the coolest dwarfs. These have surface temperatures of maybe 2,500 kelvins, or less than half that surface temperature of the sun, and there's hundreds of them for every sun-like star. What happens below that? Well, below that temperature, you have a hot ball of gas which has not got fusion occurring, so there's no energy source. But there's thermal radiation, of course, because it's still a hot ball of gas. And in this hot ball of gas, by the time the energy has diffused out and leaked out into space, that surface temperature is now going to be maybe 1,000 degrees Kelvin or 800 degrees Kelvin. Now, of course, that's not very different from the temperature of a hot planet like Mercury. So these are stars that are not generating their own energy by fusion. And in fact, they may be slowly collapsing and generating energy by their collapsing. And they're not going to shine invisible light at all. They will have the bulk of their energy coming out at infrared or even far infrared wavelengths. And so I think the word brown dwarf came because, in a practical sense, there'd be a panchromatic view of the radiation so that it would be a kind of muddy brown color. But that also conceptually and perceptually to the eye, that's what the dimmest reds tend to look like. So that's where brown dwarf came from. It's not a star, it's a cooling object, a gas cloud. The endpoint of that cooling is a black dwarf. So back to the question, because eventually that star will radiate away all its energy. There's no energy source there from fusion. While the star may collapse and gain in energy because of gravity, if it reaches an equilibrium state, then eventually it'll just radiate all its energy away into space. And it'll do so and take an infinite time to do so. So a black dwarf, a true black dwarf, emitting no radiation, can only happen after a substellar object has existed in space for an infinite amount of time. So it's a sort of almost a theoretical idea of black dwarf. Have we seen objects like this? We've definitely seen brown dwarfs. So brown dwarfs, which is to say objects just below the stellar mass cutoff, the mass to be a star, which is about 7% the mass of the sun, they've been definitely detected. First time a couple of decades ago. A lot of debates over false detection, and it was a controversial subject for a while, but with the Spitzer telescope and infrared observations from the ground, there's no doubt we found brown dwarfs, but not large numbers. They're very hard to see. You can only see them in the nearby universe, essentially. And the coolest of those brown dwarfs is at a temperature probably similar to the number I gave, 800 or 900 Kelvin. So that's nothing like a black dwarf. That object would have to cool for trillions of years before we'd be tempted to call it a black dwarf. Does that mean black dwarfs don't exist? Absolutely not. They could exist. They would have to be pretty low mass objects. In a sense, the universe hasn't lived long enough to create true black dwarfs because it's only 13.8 billion years old. The universe will have to be alive for hundreds of billions or maybe trillions of years for there to be true black dwarfs out there to find.
All right, the next question is from Julian. And the question is, do astronomers still use and operate telescopes, or are the telescopes now all managed by technicians?
Yeah, that's a good question, and because it's a part of my own evolution in the subject, and it's a thing that astronomers of different generations debate. The question of, how hands-on astronomy should be, or does it, or needs to be. Now, so the simple answer to the question is that almost every telescope above 3 meters in size anywhere in the world is operated by a night assistant, a telescope operator, and will almost always have a technical crew on hand during the day and one on call at night in case something goes wrong. By the time you're up to a 10-meter telescope, or an 8 or 10-meter, the big telescopes, then there's one telescope operator, and there are technical people on hand throughout the night. The time is so valuable that there may even also be a programmer as well as an engineer available at night, and then during the day there's a whole day crew, possibly 8 to 10 people with strong technical skills. So for those telescopes, which is the bulk of the world's research telescopes, the astronomer does not drive the telescope. In fact, is not supposed to, is not allowed to. I mean, the regulations of the observatory, if you're a visitor of the Keck telescope, say, or the Gemini telescope, or our telescopes as a visitor, do not allow you to drive the telescope. It's not just simply a liability issue. It's simply that the average astronomer is not well enough trained, and the telescope is complicated enough that they wouldn't know if something bad was going wrong. So that's the simple truth of research-grade telescopes. They're not driven by the astronomer. And there are also no eyepieces, so that romantic notion of looking through a telescope, that goes away as well for all the large ones. And that's even more true, of course, of space observatories, which are not controlled by an astronomer with a joystick or at a control room. They're entirely operated by the staff of those observatories, the Hubble, the Spitzer, the Chandra, and so on. And below 2.5 to 3 meters, then you are still in the realm where people, we have telescopes like that. We have 40-inch, 60-inch, and a 61-inch, and the 90-inch on our local mountaintops. And the 90-inch has a telescope operator, but those smaller ones don't. And so astronomers operate those telescopes, and that's how our graduate students get training. Many graduate programs around the country in astronomy don't have their own telescopes or access to small telescopes. So there's a whole generation of students, really for the last 10, 20 years, who've not, unless they had the side interest as amateur astronomers or they grew up with small telescopes, who don't have that skill. It's just not part of their toolkit, which is slightly unfortunate, and hence the debates of faculty members and astronomers over whether the generation of people who come into the subject without having done hands-on astronomy are missing something important. And this is not just some misty romantic notion that, you'd be good to just stare at the stars and know how a telescope works and be able to use it yourself. It's a little more than that, because when you deal with data that's disembodied, where you weren't part of the taking of that data, where the instrument was controlled remotely, where the telescope was controlled remotely, and you were only diagnosing what's going on after the fact, or through the data that's delivered to you, rather than things that you might see in real time, and questions you might ask in real time, and troubleshooting you might do in real time, you're limited. There are some limitations to what you know about your data. And so that's a fairly profound issue that is, I think, a legitimate object of concern for professional astronomers, whether by being removed from the guts end of the data taking, which, yes, involves steering the telescope, but also involves knowing the weather conditions extremely well, knowing any glitches or strange behaviors of the instrument, because you're right there and you know what's going on. Losing that is important. It wouldn't be as big a deal if astronomical instruments were so seamless and uniform in their operation that you always got the same data. If everything was completely reliable and the same, then it maybe wouldn't matter. But astronomical instruments are not always the same. They don't always behave the same. They're sitting in a difficult physical environment of changing temperature and humidity, of static electricity and all sorts of things going on a mountaintop, high altitude and so on. So being proximate to your data when it's taken is a significant advantage, and that is one that is now eroded with time.
Okay, the last question for today is from Carlos, and he is interested in the connection between the Big Bang Theory and wonders what are the possibilities of parallel worlds or parallel universes.
So the extensions of the Big Bang Theory are under active investigation now. So since, as mentioned in an earlier question, the Big Bang is a fairly mature theory. There's a lot of evidence to support it, even as we remain ignorant about dark energy and dark matter, the driving forces of the universe. And now there's even significant evidence for the inflationary epoch of the very early universe that stretched out space-time, making it flat and smooth, as we observe. The issue of space-times beyond our own, or the multiverse idea, there's a related concept. It's now on the table of cosmology. So it's in view, and it's sort of one of the next steps if you wanted to push the theory and ask a deeper question, not just the question of how did the universe begin, because that's the Big Bang Theory, But how did the universe begin, or why did it begin, or was there more going on than this one iota of space-time that exponentially expanded and then expanded at a more leisurely rate and created all the structure we see, including ourselves? So these are legitimate cosmological questions now that we have a mature theory and we're not sort of second guessing it or wondering whether the steady state theory is right after all. There's no great competitor to the Big Bang theory around. So astronomers and cosmologists and theorists in particular are liberated to ask these deeper questions. So absolutely, it's where the frontier of cosmology sits, but it's a very tough frontier to penetrate with data, with observation, and that's really the problem. The theory of what might be going on beyond our space-time, or what it might have been the precursor state of the Big Bang, there are theories of that, and they're based on string theory, quantum gravity, other things I've alluded to that are frontier theories in physics as well. But there are no single theories for those ideas. There are many possible string theories. There are many possible quantum gravity theories. There are many theories for the topology of space-times beyond our own, that is, their shape and connectedness, as commented on in a previous question. So there's no single theory to test even. There's a suite of theories, and they're all at the limit of physics, where our physics is not secure. So that's the theoretical issue. The observational issue is, how can we test them? How could we show that there's space-time beyond our horizon? How could we show that there were other universes, if we want to talk about it that way, or maybe other space-times that expanded and contracted? And at the moment, if you ask the hard-nosed question, can any of those bigger theories in the Big Bang give us a predicted thing that we can go out and measure? The answer is no. So I'd say the multiverse idea, the source of your question, is on the table, and we're sort of looking at it, checking it out, trying to figure out a way forward, but at the moment there is no test. There's no set of observations that we could use for our large telescopes or our future space missions that will test this idea. I think it may be 10 or 20 years away, and it may need better theorizing to make such an observational test manifest. But thanks for the questions, and thanks to you all for participating.